Hello and welcome back. Let's move on from integrals and start talking about some parametrization. So we might ask ourselves what exactly this is or why we might use it. There's a lot of applications in Calculus 3 that you'll get to see if you watch that series when it comes out. But for now, I'll just tell you what it is. Basically, what parametrization is it's a way to represent, in this case, a line. In Calc 3, we will also talk about parametric surfaces. But in this case, representing a line in two different functions, x and y, that are functions of another variable. So, two functions, x of what we usually use, t, and y of t, and these will give us different things. So certain case we might use is something like projectiles in physics. Let's say if we had a little cannon here and it was shooting a cannonball and we wanted to know how does that cannonball, how does the position change? Well, we would usually write one equation for how does y change according to time and how does x change according to time. Of course, x would just be the starting velocity going this way, and y would actually be the starting velocity, and then we have to take gravity into account and everything. So that would be one great example that you might have seen before if you have taken physics. So let's just practice trying to find parameters for certain lines. So the first line I have for us, or actually first we're not going to find the parameters. First we're going to find out what the line is from the parameters. Then we're going to get a line or some type of curve that we want to find the parameters for. So our first one is x of t equals t and y of t equals t squared. This is very simple. We can just say x equals t and y equals t squared. And well, if x equals t, we can substitute x into here, y equals x squared. This is just a basic parabola. So that's an easy one. Let's get on to maybe something a little tougher. Although I am sure we have all seen this before. Let's say x of t equals cosine of t and y of t equals sine of t. This is very interesting. Now what we're going to end up using is a trig identity, specifically your Pythagorean identities. But you might notice these are actually the parameters for the unit circle. So let's put them together. If we let x equal cos t, which it already does, and y equals sine t, we can square both sides on the x. We get x squared equals cos squared of t. And let's say we know that 1 minus cos squared equals sine squared. Let's just put this down to remind ourselves. Y squared equals sine squared of t. 1 minus x squared equals 1 minus cos squared of t. I just times by negative 1 on each side, and then added 1 on each side. Very simple stuff. And we know that 1 minus cos squared t, well, that's sine squared t. Sine squared t is y squared, so 1 minus x squared is y squared, and we do indeed get the equation for our unit circle. a circle, radius 1, centered at the origin. And in case you don't know what I'm talking about, it's just this. Very simple. And our t would be the angle coming out from here, in radians, of course. And this point right here would be cos t sine t. And so that's what our parametric equations are telling us, is that we can find x and y easily on this circle by using these functions. So that's our last example for going from the parametric equations back to a regular plottable equation. So let's try to do it the other way. Now this is where things might become a little tough, but I hope I walk you guys through it slowly enough so that you can really grasp the concept. So first, let's parametrize this line, going from 0, 0 to 1, 5. Now this might seem as a daunting task because the line isn't actually an equation and it stops. It has a range. In specific, x ranges from 0 to 1. But we'll see how we find these equations. So first thing with a line, what I like to do first is let t range from 0 to 1. And this will make it a lot easier for us because now we can use the equations of a straight line. X of t equals t delta x plus x initial. And same for y. Y of t equals t delta y plus y initial. What do these equations mean? It might not stick out to you in the start, but let's just plug some values in and I'll show you what these values mean. Our delta x goes from 0 to 1, so it's 1 minus 0, that's just 1. So it's just t times 1, which is 1. Our x initial is 0 because we're going from here to here. Maybe I should add some arrows here so that you guys know exactly what I'm talking about. And then we've got y of t equals t times delta y, which is 5 minus 0, 5, 5t, plus y initial, which is 0. And let's just check our work here to make sure. We know x of t equals t, so x equals t, y equals 5t. If x equals t, and t ranges from 0 to 1, x also ranges from 0 to 1. Our y just equals 5x. And we can see that is exactly what our line is. X from 0 to 1 going up 5. I apologize for not having a proper slope there. But let's get into a little bit of a different one. I'm going to leave my Cartesian coordinates here. Now let's find this line segment. this is y equals x squared, and we're going along the line. This, just realized I could be drawing this much better. Our line is just going like this. So this is actually quite easy. We can see that we already have y as a function of x, and that is x squared. And x just equals x. So we could actually write it as x as a function of x equals x. Because for every value of x, x just equals x. That's always true. So now all we have to do is replace our x's with t's, and we get y of t equals t squared, and x of t equals t. And we can check our work the same way. But first, I forgot something. We have to notice that x runs from 0 to 1. And since x just equals t, t also runs from 0 to 1. Very simple. So that's our second last parametrization. Let's do one more. Let's parametrize this line. A circle with a radius 2. The complete circle. Well, this is actually just as simple. This is really just, for any circle, we have x of t equals r times cosine of t, y of t equals r sine of t. And for the full circle, we know, coming from the unit circle, that t runs from 0 to 2 pi. If we wanted the top half of the circle, t would run from 0 to pi. If we wanted the bottom half of the circle, we could have t runs from pi to 2 pi. And the same goes if we just wanted a little tiny slither of the circle. That's totally fine. So, let's figure out what's our r. That's 2. So x of t equals 2 cos t. Y of t equals 2 sine of t. Very simple stuff. And that's parametrization, but I'd like to talk to you guys about one more thing, parametrization. As you may remember, we talked about arc length a few videos ago, where we said that our arc length, little s, is equal to the integral of a small segment of arc length. Essentially, just a sum of all the little tiny pieces of arc length. And we said that ds, we derived this, is root dx squared plus dy squared. But we said this isn't specifically possible to be evaluated until we times by dx over dx. And so for that, we got 1 plus dy over dx squared dx. But let's do it with parametric equations. Well, all we have to do is times this by dt over dt. Bring the dt into the root the same way that we just used to. We have dx over dt all squared plus dy over dt all squared dt. And so this gives us something very interesting. In fact, this exact ds is used in Calc 3 when we talk about line integrals. Let me just show you a little thing I have on my desk here. This is a line integral, an integral over 3D space. And this is exactly why this is very important. So let's find the arc length of our circle radius 2. Now we know the circumference of a circle, but let's just do it this way. So S is the integral of ds, which is this, which is the integral. Well, our x of t, I should have kept these up, is 2 cos of t. Our y of t is 2 sine of t. And t runs from 0 to 2 pi. So our bounds of integration are actually going to be 0 to 2 pi. Now, let's find dx dt. Well, dx dt is negative 2 sine of t. What's that? Let's square that. We get 4 sine squared of t plus dy dt, which is 2 cos of t. Let's square both sides like we do under here. And what we're going to get is 4 sine squared of t, cos squared of t, 4 cos squared of t, dt. Very interesting. We get a sine squared plus cos squared, that's 1, times root 4, that's 2. So we just have 2 integral from 0 to 2 pi of dt. This is just 2 times 2 pi minus 0, and we get 4 pi. Why is this very interesting? Well, that's because our circumference of this circle equals 2 pi r. What's our radius? 2, that's 2 pi times 2, which is 4 pi. Exactly what we got right there. And so parametrization becomes very useful in Calc 3 when we want to integrate over 3D space and we want to find a very small section of our line segment. And this is exactly what I'm talking about. I'm not going to get into Calc 3 too much because we will be starting that series quite soon, actually. There's only a few more units. And so I hope to see you in those. And I also hope to see you in Calc 3 when we come back to this, something very, very exciting. Thanks for watching.